Okay, let's say you have these parametric equations. Now, let's just think about what these parametric equations tell us. Now, the problem is just find a vector in the direction of the line, and then find the distance from the origin to the line. Let's go ahead and visualize the thing a little more in detail. First of all, this tells us this is a line through the point -3, 5, -4 in the direction (2i minus 3j plus k). Okay, if you understand the basic picture that we did last time, this is pretty obvious, so I'm not going to go over the details of it. Just, you can immediately see this. Okay? Because, well, I mean, the vector (3i plus 5j minus 4k) goes from the origin to this point. Okay? And then you take whatever parameter you want to use, of course we use t here, and multiply it by this. And that equals 2t minus 3 times I plus -3t plus 5 times j plus well, or am I? T minus 4 times k. So here's your x, here's your y, here's your z. Okay? Well, just in understanding what this means, and let's just, just review the whole thing. Another way of writing these equations if you solve each of these for t, you get the symmetric equations. These are the scalar equations. Anyhow, the symmetric equations, t, you solve for t, you get x plus 3 over 2. Solve this for t, you get let's do -y plus 5 over 3. Okay? Multiply both sides by negative, and then that would be, then that equals z plus 4. So you have this system of equations, which is totally equivalent to this, which is totally equivalent to this picture down here. Okay? You want to be able to see it all three ways, because depending what you want to do, you're going to want to, well, that's what you're going to want to do. Now you can just read it off. There's a rule that says that, there's your vector, and there's a point, okay? But if you don't understand where that comes from, you're going to be shaky on that rule. If you understand where it comes from, you're not going to make a mistake. At least you're much less likely to make a mistake. If you're like me, you're probably going to make one anyway, but you'll understand what you did, and you'll be able to fix it. Okay. So, now the problem is, well, first of all, you've got your vector. The problem asked for that. Didn't ask for all this other stuff. But anytime you see one of these, you want to think all this. You maybe don't need to write it out unless it's going to be useful, but you need to see that whole picture. Okay, now distance from the origin. So we can sketch this. You have the point 2, -3, -4 here. So here's 2, -3, -4. And we can sketch that. Maybe I ought to put it about here. Anyhow, that's our point. Now you can do a vector from the origin to that point. Of course, that's a vector that I've already written down here. This is a vector from the origin to this point. And now you've got the line, which is in the direction of the vector 2, -3, 1. So that would be 2 this way. Wait a minute. Let's talk about mistakes. And I looked at the wrong vector. Let me redraw this. Okay, be a little more careful with it. The point's -3, 5, -4. As seeing the point is this because I'm looking down here. -3 is over here. 5 is over here. So okay, there's -3 in the x-axis, 5 in the y-axis, and then -4. So we come down 4 units here. So there is our point. Let's see, our line is going to be in the direction of 2, -3, 1, so it's going to go up like that, so I can label it here. Label the point. Then we have the vector, which comes out 2 units in the x direction, -3 units in the y direction, and 1 unit in the k direction. So I can kind of do this, and then here's a vector. That's this vector in the direction of the line. Now we want to know the distance from the origin to this line. The distance from the origin to the line occurs on a line segment that's through the, starts at the origin, we'll say, and ends at the line and is perpendicular to the line. So wherever that line is, if this is perpendicular, then the length of this segment is the distance from the origin to the segment, from the origin to the line, okay? So okay. Now what we know is we have this vector here, and this vector is that -3i plus 5j minus 4k that I became aware of when I interpreted this. Okay? In other words, this is the point, from the origin to the point is this. So now we've got a right triangle. So here's a right triangle, and the projection of this vector onto this direction, or onto this, onto, let's say, even the line from the origin to the line at a perpendicular is going to be that distance. Well, there are a couple of ways we can get that. We can use a cross product, we can use a dot product. Okay? We do a cross product of this with this, and it'll give us a vector perpendicular to both of these. Or we just draw the triangle. We can do the dot product. Well, we can do projection of the 3i plus 5j minus 4k, it's negative 3i. Projection of this vector onto this vector this vector here is 2i minus 3j plus k, we're going to label that. Okay. That projection is just the dot product of these vectors divided by the magnitude of this vector. So we can see that, let's say here's a vector, just bring it, bring this out into a plane, just change our orientation. We have the vector, well, let's just say this is a vector v, and here is a vector w. The projection of v on w is this. Projection onto w of v. Now, this angle is theta. We're using theta for the angle between the two vectors, as usual. Okay, there's your angle between the two vectors, and it's pretty clear that the magnitude of this projection is the magnitude of v cosine theta. There's your hypotenuse. This side is the adjacent side, and it's side adjacent to the angle. Just your cosine. Well, okay, there's your projection. The dot product, v dot w, is magnitude of v, magnitude of w, cosine theta. So how does this compare to this? Well, it's the same, except you got this magnitude of w in here. So projection of v on w is just v dot w over the magnitude of w. Okay? And another way to look at that is that's just v dot w over the magnitude of w. In other words, you reduce w to a unit vector, and then just do the dot product. Looking around this, I'm going to close that. Okay? So we can visualize this process as just v projected onto a unit vector in the direction of w. So let this be unit vector u, we'll use u for unit. And that's just w over the magnitude of w. And the projection and let me back up a minute. The projection is actually a vector. I got an arrow over the projection, so I should have absolute value signs around all this. Cosine theta can be greater than 90 degrees, which will give you a negative cosine. Okay, it's not too simple. So the magnitude of the projection is this. There's also the vector projection. the magnitude of the projection onto U of V equals the magnitude of V dot U. The vector projection, you take the scalar projection, but with a sign, cosine theta, and you multiply it by this unit vector. So that the vector projection is this multiplied by a unit vector in the direction of W. So you take the vector projection, which is how long this thing is, you multiply it by a unit vector in the direction of W, and you get a vector. You get this vector here. Okay, vector projection. Now, all that is in the section that you just did, and you got all the problems right and everything, okay? Let me try to bring it into a little perspective. I could have organized that a little bit better, but what we were doing originally was just this problem, okay? So I've kind of digressed to all this machinery, but it's relevant to this problem. So here's your vector projection. Now your book will give you formulas for all this stuff. The formulas don't entail understanding. Okay, the formulas represent something you want to understand more deeply. Another way of writing this vector projection, which the book gives you in a formula, this tells you the V dot W over magnitude of W is just the length of this side, but maybe it's negative because the cosine might be obtuse. In other words, if you have V here and W here, here's your theta, then the projection goes this way, and it's in the negative direction relative to W. Okay? So the vector projection takes all that into consideration. And the book gives you a formula. I like to do this as this, which is just how long this vector is, multiplied by a unit vector in the direction of W. Okay? Because that tells you what's going on. Your book, and just about every textbook, wants to represent this in more compact notation as V dot W over the magnitude of W squared times the W vector. This obscures the intuition you get if you see this as it is, as how long the vector is times the unit vector in the direction of W. Well, how long it is and negative if the angle is greater than 90 degrees. Okay? So, recommend, if you understand these pictures, be able to reconstruct them anytime you need them, because if you do, it gives you pretty much the whole picture. Now let's bring that back to here. Okay, so we project this vector on this one. So we project this vector on this vector. And that's going to give us so let's say this is your three I plus 5j minus 4k, the vector from here to here. And then you have this vector. And let's see which one of those is long. This is actually a little longer, so draw this like so, and then we do the projection, and naturally we extend this vector. This is your 2I minus 3j plus k. And remember that came from these three numbers, the way you want to understand. Well, that projection is going to be this. Is going to be the vector projection. So let's call this vector v, this vector w, and this is the projection onto w of the vector v, and it's a vector projection. Okay? Now, there's another vector involved in this triangle, which is maybe this one. I mean, it is this one, maybe I'm going to call it purple. It's the length of this vector that's the distance from the origin to here. So in this picture, here are the three dimensions. Same vectors. Would be like this. Okay, this and I drew this backwards, this angle. Got the heads of these vectors in the wrong end. Oh, no. This is blue. So now I can say what I was about to say. This plus this equals this, right? So this vector, okay, if this plus this equals this, then this equals this one minus this one, right? So this vector is v minus the projection okay. So it's a magnitude of v minus the projection, that being the length of this vector. And that's easy to calculate. You just do the projection. Projection is just this. Well, it's the vector. It's the vector you get up here from this vector and this vector, okay? So it's easy to calculate. You just do a dot product and the magnitude of the second vector and subtract that from v. Now that's a little more complicated than the way the book does it, which involves a cross product, okay? And you can read that, if you're not clear on it, we can go over it next time. But the geometry of the thing is just the same, okay? The cross product is convenient because it automatically gives you a vector perpendicular to the line. So you just project this vector on a vector perpendicular to the line, and you get it. It's a different way of using it. We use the cross product to get a vector perpendicular to the line.